Professor Francisco. Professor Francisco is currently a full professor in electrical power engineering and founder and leader of Digital Energy System Laboratory at the Department of Electrical Engineering, Information Technology, Cybernetics at University of Southeastern Norway. He is author and editor of several books in Spanish and English, and his research produced 20 plus book chapters, 40 plus journal articles and magazine papers, and 100 plus conference papers. His research interests include innovative operational control schemes to optimize the performance of future energy systems. I would like to request Professor Francisco to please share his presentation with us.
Thank you. Thank you very much for your very kind words and the nice introduction. Could you please confirm if you can see my screen right now?
Yes, we can see your screen and can hear you loud and clear.
Okay, thank you very much. Well, it's time to start this presentation today. I would like to start saying thank you very much to the Industrial Electronics Society in Western Australia chapter for the invitation and for giving the opportunity to share some experience here with all of you. Also, I would like to say thank you to everyone that is attending to this webinar, and I would like to say thank you for sharing your time and be so kind to be here, okay? Initially, before I start, I would like to say that all the opinions here in this presentation belong to me. I don't have any commercial relationship with anyone, and all the responsibility about any kind of opinion or any kind of information is totally on me, okay? The other thing that I would like to clarify before we start with the presentation is, as usual, I love to put the videos of the webinar at my YouTube channel. I want to be you aware that I am recording this presentation, only the presentation, okay? And it will be uploaded in my YouTube channel using high resolution 4K. And also the slides, it will be available at my research gate, okay? It will be easy for you, download the slides from there, and all the slides have documentation that you can follow later. Before I start seriously this presentation, I would like to start with a preamble, okay? Just a very interesting note, okay? I was looking to the newspapers yesterday, and I realized a very big event in Australia, and it was a frequency event, and it's related with a very bad situation in a coal-fired power plant. And there is some newspaper that say that it was caused by this coal-fired power plant and create a blackout in Queensland, okay? I don't want to start this presentation with bad news. Otherwise, I want to start with good news, okay? I believe for me, this is a very nice moment to be in Australia talking to you, because this is the area that I love to talk about. I love to talk about frequency control. I love to talk about future energy systems. And well, right now it's very, very interesting, the situation happening in Australia, okay? However, I must be honest, I'm Australian. I don't have full experience about Australia. I will try to do my best to present the information about the topics that I know, okay? And the first step here is I will present the agenda. But before telling you the full agenda, I would like to say that I try to minimize as much as I can the number of equations and numerical results that I will show in this presentation. The idea is that this presentation is for general public with few understandings about electrical power system and frequency control, okay? What is the starting point of this presentation? Well, I will start with a very short discussion about the paths to reaching the net zero carbon emission, okay? Then I will discuss some aspects related with the energy transition that is happening in many electrical power systems around the world. And I will discuss some of the issues related with this transition, okay? This transition is happening in many dimensions inside the electrical power systems, but I will focus basically in one of the aspects that I have a very good understanding, okay? And that is the consequence of the reduced levels of synchronous generation. And I will discuss three of those points, the reduction on fault levels, the situation related with the limits of reactive power and also some voltage control. And finally, my favorite topic, that is the reduction on rotational inertia. And the second and final part of this presentation will be related with some methods that they are already well known around the world in order to enhance the system stability. And basically, I will discuss two different types of methods. Some methods related what I call the short-term or mitigation measures. And then I will discuss what I call the long-term, okay? And finally, there are some closure remarks, and that's all. Well, let's start this discussion about what I call the path to net zero, okay? As you must be aware, there is a situation related with the climate change, and many countries around the world, they are already committed to reach what we call the net zero emissions, okay? There are many countries around the world. There are some countries that they already achieved the zero net emissions. The case of Bhutan, a couple of weeks ago, I was in Bhutan. But they are also very big and industrialized countries that they are already defined limits for the for reaching the zero net emission, okay? The case of the UK is very well known. 2050 is the year that we are enforcing the zero net, but also there are very interesting cities inside the UK where we propose reaching net zero before 2050. That is the case of the the Scottish city of Glasgow, 2030, Manchester, the son of you must know, 2038, and Bristol, 2030, okay? The general rule is for the European Union, 2050. And I believe, if I correct, in Australia, I read some commitments for 2050, okay? The interesting thing is that reaching this zero net emission is a big challenge for many countries and for many sectors, okay? Because many sectors are required to change the way that they are producing energy. And in the case of the electrical power system, well, we are committed to reduce the emission by 2050 in the case of National Grid, the TSO of the United Kingdom. And we are pushing very hard to reduce those emissions, okay? As you can see over here, there is a Climate Change Act that is the law that is enforcing that we need to reach the net zero by 2050. And over here, you can see there is a small link here down where you can go to a website, and there is a tracker where you can see the numbers related with the CO2 emissions, okay? The interesting situation here is that I think somebody has the microphone open.
I will mute everyone, and Professor Francis, then you can unmute yourself. I'll mute all.
Okay, yes, please.
Yeah, I have muted all.
I am unmuted myself. Could you hear me?
Yes, we can hear you.
Okay. I was here talking about the commitments of the UK regarding the CO2 emissions, and we have reached a very interesting point here regarding the CO2 emissions. Okay, there is a record in this year about reaching only 39 grams of CO2 per kilowatt hour. That is a very impressive. That is a very impressive reduction on CO2 emissions. Okay. But the interesting thing here is a few days ago, a couple of weeks ago, the IEA, that is the International Energy Association, they published a roadmap regarding the CO2 reduction, the pathway to get zero net carbon emissions by 2050. And I highlight here several of the aspects that I believe they are extremely important for us, okay? For us, for electrical engineers, I can see that there are several aspects over here that they are very important. One, we need to push more about solar power production and wind power production. And second, that is a target. There is a target for 2030, about 1,020 gigawatts coming from this primary energy resource. But also there is a deadline for 2035 to defining that the economies must be reaching the zero emissions in the electricity sector, okay? And by 2050, in theory, 70% of the electricity must come from these kind of renewables or not, or environmentally friendly energy production, PV and wind power, okay? What is the main remarks here? The main remarks is we are moving in this direction of reduction of massive reduction of CO2 emissions, and the electricity sector, the utilities, they have very important milestone that they must reach, especially regarding production of energy coming from renewable resources, wind power mainly, and PV, okay? But let me go back, let me go to the next slide, okay? Right now, the question is, okay, there is something that is changing. There is something that must be changed by 2050. What is about this transition? Well, this transition, there are many people talking about this transition, but for the electricity sector, for the power utilities, the transition is a high challenge or a very big challenge for the utilities. Why? Well, there is a very big issue, and it's, okay, we want more renewables into the electrical power system. We want more energy efficient solutions for the electrical power system. We don't want those very old, inefficient, and polluting power plants. But the problem is that those very old and probably some of them polluting power plants, they use the classical synchronous generator. And the classical synchronous generator is one of the most very lovely elements inside the electrical power system. They have a very basic but beautiful performance, but the problem is we are disconnecting those synchronous generators. And to substitute those synchronous generators, well, we are using these lovely, environmentally friendly solutions like wind power plants, PV power plants, and also there is a new actor, the energy storage system. And those technologies, they have something that is very important. First characteristic, they are highly dependent on the weather. I mean, wind power plants require wind, and PV power plants require solar energy. And second, they have what we call power electronic converters. They require some sort of mechanism in order to produce the signals that they provide the electricity into the electrical power system. This slide over here is a huge summary about the different directions where the electrical power system is changing, okay? This figure is taken from the Institute for Energy, Economic, and Financial Analysis, And they clearly established that the power system, the power utilities, they are changing in many directions. They are changing the way that we need to operate the power system. We are changing the way that we are producing electricity. We are coming from very large power plants with very big synchronous generators. We are moving from smaller generation units with highly distributed, that they are highly distributed inside the electrical power system. And many of them are using what we call the power electronics, okay? From the transmission point of view, again, there are some changes. We are moving from those very large transmission lines. We are moving for more use in the small assets. We are talking about distributed generation inside the distribution systems and so on. And especially on the demand side, the customer side, we are changing, okay? We are changing the way that we produce electricity. We are including more renewables. There is something called energy storage. And on the customer side, on the demand side, also we are changing. And the good news on the demand side is that the demand side used to be highly stochastic, but right now we are including many components inside the customer that they can be more active, proactive into the electricity sector, okay? What I'm telling you is that the customer right now is more concerned about the way that the electricity is produced, more concerned about prices, and those customers, they are changing for prosumer. Somebody that is active, that is willing to produce electricity and also selling the electricity to the electrical power system, okay? But what is the core of this transition for my presentation today? For my presentation today, the problem is that we are using power electronic converters more and more. And this is something that many countries around the world, they are facing those challenges. I will say that one of the countries that is facing this challenge for many years has been EirGrid. That is one of the transmission system operator in Ireland, okay? EirGrid has been facing the problem of a lot of wind power, very high wind speed, reduction on the demand, and then they need to take actions because the variability coming from the wind power plants must be reduced, and sometimes they need to disconnect these wind farms, okay? They have been very concerned about the penetration of power electronic converters, and they were first to introduce this concept, the SMP, the SNSP, the system non-synchronous penetration. This is a definition you can find in the document that I'm showing you here below. There is a small link here that you can follow, and you can find the full definition, okay? But the SNSP, is basically an index that allows to define the penetration of non-synchronous generators. And the penetration of non-synchronous generation is coming from different point of view. It can be double-fed induction machine in the case of wind turbines, full converters in the case of wind turbines, but also in Ireland is quite good. It's quite useful, the use of HVDC interconnectors. For that reason, this index over here is taking in account the non-synchronous generator plus the interconnectors, and is divided by the demand and the interconnector support, okay? This is a basic formula, but this formula has very important implications. And let me go to the next slide to show you the implications, okay? If you look this plot over here, you can see that in this plot, we have a vertical axis, and the vertical axis is defining what we call the denominator of this expression, the SNSP, okay? You can see that this vertical axis corresponds to the demand and the support using megawatts, and the horizontal axis is basically wind power plus import, okay? That is basically the numerator of this equation. And what are those plots in green color over here, in yellow color over there, and red color over here? Okay, those plots over here, those straight lines over there, you can see that there is a percentage over there, and that is the percentage, the penetration of system non-synchronous generation, okay? And what is the importance here to take away? Well, the importance here of this plot is that initially when EirGrid think about this plot, they were working in this area over here. basically medium to a small penetration of non-synchronous generation. But when you reach this level over here, the operation start to become very, very difficult, and that is where air grid have to take actions. One of the classical actions used in the past was the classical curtail of the wind farms, okay? That means stopping those generation plants or stopping those generation plants to be a part of the generation mix, okay? Well, let me move and I will present a plot that right now all my colleagues here, all my Australian colleagues, probably they know this one, okay? Because this plot over here is the clear demonstration that this is a very exciting moment in Australia. Because the National Electricity Market Engineering Framework in 2020, March 2021, indicate in this plot how important has been the growth in wind power and solar power into the Australian power system in the past decade, okay? In this plot over here, you can see very important highlights, okay? As you can see over here, there is a high penetration of wind and power. You can see that we have reached around 47% in 2019, but also around 52% in 2020. Okay, we are talking about that the number of generation units using power electronic converter have reached more than half of the total generation. And also you can see something very interesting, and that is the minimum value of synchronous generation. What I'm trying to tell you is right now the transition is a reality, and probably more than a transition right now in Australia, because Australia is receiving more and more penetration coming from renewables, but at the same time, the number of synchronous generation connected, they are decreasing, okay? Well, we have talked about the reality and the evidence that the number of power electronics generation base has increased in the recent time. But what is the problem? What is the issue of having so much power electronics inside the electrical power system? Okay, this is a funny slide. Sorry if you are laughing right now, but the situation that we have right now in many power systems around the world is that we are disconnecting synchronous generation. We are reducing the number of generation units connected to the electrical power system, and instead we are connecting more and more power electronics. And what is the issue? The issue is that they are totally different, okay? To be honest, this is a horse here. You can see this is a horse, and this one is a zebra. They belong to the same branch, but they are different species, okay? They look like a horse with with white and black stripes, but they are totally different. And here I would like to use that analogy to say that the synchronous generator and the power converters, they can do the similar job, but they are not the same. Okay, the first conclusion that I would like that you understand here is, okay, synchronous machine, they are synchronous machine, power converters, we can try to make the power converter to look like a synchronous generator, but they are not synchronous generator, okay? Well, moving forward, what I want to show you right now is that these differences are coming from many points of view. Okay, to be honest, the synchronous machine is a beautiful machine, very simple in design, very amazing on the electromechanical conversion process. And this machine is extremely, I will say, perfect to do the job, okay? One of the things that you must understand is that synchronous generator, they, by basic principle, they produce frequency. When the rotor spins inside the stator windings, there are some voltage induced in the stator winding, and there is a frequency. This machine is producing frequency. And when there is a change in the electromechanical conditions here, we have a change on active power. This beautiful machine will try to adapt to this change without any kind of external of external controller defining, for instance, the inertial response, okay? Of course, there are some controllers. There are some controllers in the synchronous generator. There is a frequency, a controller dedicated for frequency control or active power balance, and that is related with the governor. And there are some other control that is related with the terminal voltage or the reactive power production. But here below, you can see a very basic schematic. This is a very basic schematic of a traditional power converter. In a traditional power converter, the first thing that you must realize is here we have power electronic switches. And the first difference between a synchronous generator and this is that those switches has almost zero overloading capacity. That means those switches, they are passive components and they are very, very sensible to overcurrents, okay? And second, very important difference. In the power converter, there are some switches over here commutating, okay? I know if there are some colleagues in power electronics, probably they are laughing about my basic explanation. But here we have some commutating devices. And to be honest, all the magic about the power converter is happening with the control systems. We need to have control system to define every single functionality, starting from the very basic, closing and opening the electronic switches. Everything must happen using the control system, okay? As a consequence, what I'm trying to tell you is that those two devices, the synchronous generator and the converters, they are very, very different, okay? The interesting part here is that those converters, they can have many and many and many controllers, okay? In this case, here you can see a very basic control loop representation for a traditional power electronic converter, okay? In this case, this is a grid connected inverter. This device can work as inverter and is connected to the AC grid, okay? This is a traditional, what we call the grid following converter. Later, I will explain a bit more about the grid following, sorry, I say grid following converter, because the grid following converter requires some mechanism for synchronization, and that is where this gentleman over here start to be important, okay? Okay, but let me discuss what is the problem, what is the issue when we start to have so much penetration of power converters, okay? And there are many issues that they start to rise, okay? Here, there is a very simple and very basic summary about the issues when we start to reduce the number of synchronous generators. The first one, and it's extremely clear, is we have a massive reduction in short circuit contribution because those power converters, they have limited capacity or almost zero capacity of producing short circuit contribution, okay? And of course, you must know that the short circuit contribution is related with several aspects of the electrical power system, including protection. If you are using overcurrent protection, you need to have some levels of short circuit current in order to identify the fault condition and also to locate the fault condition, but also some aspect related with power quality. Regarding the second issue related with the reduction is the voltage control. Synchronous generation, when we are reducing the number of synchronous generation, we are reducing the capability of the power system to control the voltages because we are reducing the sources of reactive power. And finally, my favorite is that we are reducing the volume of this rotational inertia. When we start to disconnect those synchronous generator, we are reducing the volume of this rotational inertia, and that is an issue, okay? However, I would like to clarify something. I know that there are many people here in this presentation that they understand the concept about reduce or low inertia scenarios, but I want to tell you that also very important issue right now is the reduction of geographical inertia, okay? It's not only that the whole power system has a low rotational inertia, it's also where is located that lack of rotational inertia, okay? However, I don't have time to discuss this here, and we will discuss that in another presentation, okay? But let me start with the short circuit levels, okay? Reduction of short circuit levels, okay? Here you can see the horse, you can see the synchronous machine. I love these simulation results over here because here we are applying a three-phase short circuit to a synchronous generator. Everyone know this, every single bachelor student know this. The beautiful situation here is that a three-phase short circuit here create a massive short circuit. I love this 65 kA. This is 65 kiloamps. That is the maximum point here for the short circuit current. And it's very simple for everyone to coordinate or to set up the overcurrent protection for this kind of situation. But what's happened when we have power converters? Okay, let me go for the power converters because many people are around here looking for power converters. What's happened if we have the same size, photovoltaic power plant, okay? Imagine that we have the same size photovoltaic plant, and now we apply again a short circuit fault, okay? What is the situation? We have here the steady state operation, we have here the low current, and suddenly we have the short circuit. And the short circuit means that the current is going extremely, extremely low. Right now, we have only 1 kiloamp. We have only 1 kiloamp of short circuit currents. That makes very difficult to protect this PV power plant using classical overcurrent. And also, they are another very interesting issue. In this case, we are using a all converter. We are using what we call the grid following converter, and there is a PLL. The PLL is basically the synchronization mechanism that we use. And one of the big issues about the PLL is that the PLL can create instabilities, especially oscillations related to voltages suddenly after the fault during the recovering period, okay? It has been documented that in some cases, okay, we have the short circuit, we have the voltage drop, and in some cases, depending on the location, the voltage can recover and do the job. But in some very bad cases, the PLL lost the track of the voltage and we have this instability, okay? I will not discuss this. Probably somebody will ask a lot about this in the question session, okay? Here, there is a clear evidence that this situation is happening, okay? If you are not familiar with the GB system is already having this kind of issues. There are a couple documents from 2016 where we have serious concern about the short circuit level for 2035, okay? The short circuit level have started to decrease, and the main source of this decrease, of course, is coming from the integration of many interconnectors using HVDC, but also a lot of power plants using power converters like PV systems and offshore wind farms, okay? What are the possible solutions? Well, the possible solutions, I believe you can see over here. The idea is try to use some elements that allow the short circuit injection in order to try to recover the voltages, in order to create some contribution during the fault, and very important, improve the voltage recovering after the faults, okay? What is the news here? That if you look over here about the solutions that you can find, there are many solutions related with power electronics. Here we have voltage source converters in HVDC. Here we have some controllers related with static voltage compensation. And what I am trying to tell you is that if those power converters are correctly controlled and correctly set up, they can also help to solve the problem, recovering the voltage after the fault, okay? Okay, let's move forward. What's about reactive power injection? Reactive power injection is very simple, okay? If we reduce the number of synchronous generator, the traditional synchronous generator has the possibility of delivering or absorbing reactive power. That is something extremely basic to do in the case of a synchronous machine. In the synchronous machine, we can modify the field winding current, and we can override or underride the synchronous generator and change the reactive power production or consumption. However, with the power converter, also we can do that, okay? We can do that if we define the proper control. However, one of the main issues is that the synchronous machine allows the overloading very easily. It has the possibility of dissipating the overloading inside some safety ranges, but the power converter not, okay? Well, finally, in order to close this section, I will show you what is the impact of the reduction on rotational inertia, okay? Well, there are many papers talking about the impact of reducing the inertia. And one of the main problems reducing the rotational inertia is that the rotational inertia is affecting almost every single electromechanical process in the electrical power system. And from the power angle stability, transient stability, when we reduce the rotational inertia, we have the problem that the classical and critical clearing time start to be reduced. And that is a problem that we didn't have for many years. In electrical power systems, when we start to be highly interconnected, when we start to use high-speed excitation systems, the critical clearing time start to increase and increase. But right now, the situation is going to the other direction. If we start to reduce so much the rotational inertia, the critical clearing time start to reduce. And what is the main impact of this? Well, we are losing the robustness of the electrical power system, but more important, we are creating a burden for the overcurrent protection and many other protection schemes inside the power system, because they need to open and isolate the fault before we reach the point of instability. Regarding small signal stability, there is also a clear effect of reducing the rotational inertia. If we focus in two basic indicators, one of them will be the damping ratio and the other one the natural frequency of oscillation. Well, you must understand that in both cases, the increase in the inertia has a positive impact on the damping ratio and the frequency. But on the other direction is probably the worst, okay? And finally, probably this is where many utilities around the world, they are concerned. What will happen with the system frequency response if we reduce the classical rotational inertia? Well, if we reduce the classical rotational inertia in the electrical power system, there are few things that will happen very soon. Well, they are happening already in many countries. One of them is that the frequency will start to go down faster. And faster mean faster, okay? We are having right now situations in some countries where we can find ROCOF, rate of frequency, change of frequency, that we can talk about easily 2 or 3 hertz per second, okay? That is something that is very dangerous, especially for classical synchronous generator using classical thermal power plants, okay? Another thing that you must understand is that also the frequency is going deeper. The frequency is going deeper during a frequency event, as you can see over here in this plot, as you can see here in this plot. As we reduce the rotational inertia, the frequency will go deeper. That is one of the main problems. And this means that we can activate we are activating more frequently the under-frequency load shedding, with the especially consequence for the customer and a consequence the economic impact and the reliability impact for the power utilities, okay? Here in the next slide, I would like to show you something that we did with a real-time simulation, okay? Here, this plot over here is created using real-time simulation, Because many people look at the low rotational inertia. They see those plots in offline simulations, but they don't see the proper situation over here. The proper situation over here is, okay, we have a reduction in the nadir or the minimum frequency, and that is a problem, potential problem for the frequency load shedding. But if you look over there, we have more oscillations. When we reduce the rotational inertia, we have more oscillations in the frequency. And those oscillations in the frequency, they have many consequences, especially for the mechanical components related to this generation. And this is critical. We can start to break shaft. We can start to break blades and many other components, okay? And finally, before I move to the solutions, the second part of this presentation, we are almost 40 minutes in the presentation. Different scenarios. One scenario with high inertia, and that is the green color, and one scenario using the low inertia in red color. And what is the big or huge difference? I don't know if you are aware, but in a steady state, this is a quasi-steady state simulation, okay? We are talking about a simulation for a whole month, tracking the frequency deviation over this period. You can see how the frequencies start to oscillate and go deeper and higher at the same time, okay? One of the very interesting thing is that for many years, we have been considering and focusing on what we call the under-frequency load shedding. But right now, with the use of these low inertia rotational inertia systems, we have this issue related with overfrequency. And as you can see, the relationship between the maximum and the minimum value of the frequency start to be very high, large during the day. And as you can see over here, you can see how the frequency is spending more and more time outside the regulation band, okay? What I want to tell you is that many people are right now concerned about nadir and ROCOF. And in the future, we need to consider also that the power system during normal operational condition in low inertia scenarios, they can create instability problems, okay? Well, let me keep moving here and let me tell you about the possible options, okay? This slide is already presented for many people. Many people know about this slide. There is an American version and there is an European version, okay? If you go to the document from NSOE about One Vision of 2030, the roadmap about power electronic dominated power system, you will see that they are talking about two different solutions, okay? They call the short-term solutions, they call the long-term solution. The short-term solution is something that we have been doing in Europe for many years. EirGrid and National Grid, they have been responsible and they have been working, they have many working groups and they make changes on the grid codes. That is one of the first, I would say probably one of the first steps when we are migrating for a power electronic dominated power system. Then there are some other options. You can start to see that the utilities start to try to create new ancillary services. I believe that there are many other services that we can create. And also there are some countries that they start to use mitigating measures. Okay, I will explain some of the mitigating measures inside the time that I have. And finally, what is the long-term solution, okay? Many utilities around the world, they are considering two very basic solutions. One of them is synthetic inertia. I will criticize a bit about synthetic inertia in a few minutes. And the second option that probably is one of the most promising possibilities is grid forming control, okay? Grid forming control is something that is not new. The patent is probably 10 or 12 years old. I will not go in details into the grid forming classification and so on, but that is probably one of the most promising solutions, okay? Let me tell you about mitigating measures, okay? Mitigating measures, they don't solve the problem. They don't solve the problem, but they help to move forward, okay? And one of the mitigation measures that we have been taking in several countries around the world, including Scandinavia, I am also involved in Norway, and one of the situations that we are using for mitigating low inertia scenario is, of course, awareness, okay? We are taking measurements about the inertia, and with those measurements, we define minimum inertia, okay? There are different methods to estimate the inertia. There is the basic one, just basic calculating the inertia based on the number of generator connected and the inertia connected. But there are also more recent methods like continuous signals. That is the case that we are using here in the UK. That is the case of reaction technologies, okay? I will not go in details, but I would like to share this slide, okay? Because my friend Pierluigi Macarena, he is in Australia, on the University of Melbourne. I am sure that many of you have know about his name. He was one of the first to introduce the concept of frequency response security map, okay? And in this frequency security map, what he did is creating a plot where includes some requirements, some constraints, constraint related with ROCOF, constraint related with steady state frequency, and then they create an operating area. And what is the idea? That depending of the rotational inertia, you can define your primary frequency reserve, okay? I highly suggest that you read this paper. It's located here at the top. I include the photo of Pierluigi. I hope somebody comment him that I put his photo here, but also I include the reference for him, okay? This is one of the possible mitigating measures that we can talk about. Now, what is the solution that I am interested in? Well, we are almost to close this presentation, but I will tell you about the converters, okay? There are different types of converters depending of the point of view that you use for classification, but most recently people tend to use two groups. What we call the grid forming, I call them the classical one, and there are people that they call the other group the grid forming, okay? The grid following received the name because they require synchronization with the grid. They require a signal coming from the grid, and from there they attach the voltage to that signal, and they have the possibility of synchronizing and providing power. That is this converter over here, okay? Traditionally, the grid following converter can be voltage source converter or current source converter, okay? But typically you need this PLL or any other mechanism in order to take measurement from the grid and create the synchronizing mechanism for your signals. And there is another control, and that is the grid forming. The grid forming is try to imitate, try to mimic, try to create a synchronous machine using a power converter. That is the most basic way that I can find to explain a grid forming converter. A grid forming converter is basically a voltage source, and this voltage source is enabled with control loops. And many control loops can be used depending on the representation that you want to use for the synchronous machine, okay? They are synchronization, use what people call virtual synchronous machine. The virtual synchronous machine is one of the paradigms that try to reproduce 100% the operation of a synchronous machine using an emulation control, using the swing equation, and so on. There are many other mechanisms for emulating the synchronous machine. There is the power synchronization control. There is the direct power control. I can give you a couple papers that you can read, and probably you will find probably 20 different references with 20 different controllers, probably slightly different each other, okay? However, I want to tell you about the grid-friendly power converter, okay? What is the grid-friendly power converter? The grid-friendly power converter is a concept that I started to work a few years ago when starting from 2018 after the standard 1547, IEEE standard 4057 established the new version of the requirement for interconnecting distributed energy resources, okay? This standard, 1547, 2018, they established that the converters used for solar power plants, they must include some new features: voltage right-through, frequency right-through, voltage support, frequency support, ramp rates, and also include the possibility of including communication, okay, using different protocol, including also IC61850, okay? I would like to close this presentation with some demonstration about synthetic inertia and some of converters, okay? Many people believe that inertia response is the solution for low inertia systems. I don't know why electrical engineers try to make the converter behave like the classical machine, okay? The synchronous machine provides the inertia response in a natural way. It's something that is physics. It's something that is created by the machine, okay? Here you have the comparison. Here you have the comparison of the inertia power. The inertia power is basically the active power contribution that is produced when the frequency change at the stator of the synchronous machine. And as you can see over there, depending on the rotational inertia, you have different peak for the inertia power, okay? But what is the problem about inertia power? That the inertia power is connected to the inertia energy. And when the ROCOF is going in this direction, when the ROCOF is going in this direction, Jesus, previous. Okay, when the ROCOF is going in this direction, when the frequency is going down, okay, no problem. We have inertia contribution and the synchronous machine produce energy and deliver energy to the system. But when the frequency is recovering, you have this other area over here. And that is when the machine tries to reestablish the energy balance in the rotor, and it's absorbing power. What I'm trying to tell you is that one of the issues related with inertial response, the natural inertial response of a synchronous machine, is that this response is basically dominated by the ROCOF. And depending on that ROCOF, you can have the problem that during the recovering period, you have consumption, okay? Another thing that I tell you is that we are doing things in a very different way. Because in the case of a synchronous machine, you have the possibility of overload. But if you look over here, I am using a battery energy storage system, and this battery energy storage system is enabled with an inertial response. And what is the situation? Well, depending of the frequency deviation and depending of the inertia constant, you will have different contribution. But that contribution has a limit, because if you reach the maximum power of the power converter, the situation will be that you are saturating the converter reach the maximum current that they can deliver, and they reach the maximum power that they can deliver. As a consequence, this generator, this converter will never be identical to the inertial response that is provided by a classical synchronous machine, okay? Okay, we have done many simulations. We have been using batteries. We use battery to emulate inertia, and we use the inertia in order to avoid under-frequency load shedding. But one of the complaints that I have about inertial response is that you need to use the ROCOF. And the ROCOF of a frequency signal is typically a very noise signal. And that very noise signal creates another problem. And that is the activation mechanism that we will use to activate the controller. And that is the reason that in recent time, we proposed the concept of fast active power injection. Fast active power injection is a frequency controller. It's very sensitive to the frequency. we are using basically two different control actions. We are using proportional control action and we are using derivative control action, okay? The idea of using the proportional control action is solving the problem about the activation. When we have a proportional control action, we can include a dead band. And these dead bands, if we are inside the dead bands, okay, the contribution is 0. But if we have an under frequency event or over frequency event, okay, we can use this proportionality to produce electrical power and to try to compensate the power imbalance. And when we reach a maximum, we stop, okay? We keep reaching the maximum power. However, we combine this with something quite interesting, and that is the use of the differential controller, okay? With the differential controller, we are doing something similar. We are doing something similar to the inertial response, but we are including here in the front of this equation, we are including a gain, and this gain can be controlled, okay? What was the conclusion when we start to run simulations using these controllers, okay? The conclusion is that we define a composite equation, okay? You can see here there is equation, and this equation has two components. One component, the proportional control action, and one, the derivative control action. And then we start to run simulations, and what was the good news? Depending of the settings of this case, Kp and Kd, we can do many things inside the electrical power system. For instance, using the Nordic power system, we minimize the frequency deviation in a steady state, or we minimize the minimum frequency, okay? Depending of the objective function that we use in the optimization problem, voila, we can solve many different indicators. We can improve many different indicators inside the frequency response, okay? We are almost closing here. There is one paper that I want to show you. Most recently, we have been trying to use different controllers for frequency. One of the controllers that we have been using is FUSI. We use FUSI and we understand that different energy storage have different speeds, and different energy storage technology have different speeds, but if we combine in a proper way, we can get the proper frequency response. In 2018, we published a paper. We use FUSI logic controllers in order to provide enhanced frequency response using multi-energy storage system, battery energy storage system, and frequency flywheels and ultracapacitors. And finally, most recently, we have been playing around with artificial intelligence. Last year, we published a paper where we use reinforced learning, again, using multi-energy storage system, battery energy storage system, flywheels, and ultracapacitors. And what was the surprise? This agent-based solution provides better solution than the FUSI controller and the classical PID controller. Well, I am 3 minutes on the top of my deadline. Sorry that I took so much of your time. I would like to close this presentation with something that probably will be funny for you. And I believe that probably we are doing something wrong, okay? I don't know if you can see, I start telling that horse and zebra, they are different. And here I have a horse with a zebra costume, or because I didn't find a zebra with a horse costume, okay? Because what is my message? My message here to close this presentation is probably something that you will not agree with me, but this is my personal opinion. Power converters, they are amazing. They can do many things if you design the controller in a proper way. And to be honest, the power converter is many times faster than the classical electromechanical synchronous machine. As a consequence, if the power converters are so fast, why we need to make the power converter replicate the behavior of the synchronous machine? I mean, in this transition that we are working right now, we are moving in a path where the synchronous machine reduction has been substituted by power converters. In this stage, it's clear that probably making the power converters replicate the behavior of the synchronous machine is probably the best option. But my question is, imagine that we reach the level of 80 or 90% of power converters and 5 to 10% of synchronous machine. Do we need to keep attached to the concept of traditional frequency controllers? Can we do something different? Can we start to make the synchronous machine behave different in order to match the behavior of those power converters? Well, I would like to close this presentation with this very, I will say probably futuristic and crazy opinions about power converters in the future, but we need to think about possible solution for the future. I don't believe that I will see in my lifetime this situation of 100% converters in a real big power system. What I'm telling you, I don't see realistically in the next 10 or 20 years 100% power converters in the European Union, because we are still having, for instance, France with a lot of nuclear power plants, and they have a lot of synchronous generators. But we need to think about this, okay? Well, this is everything from my side. I think it's time for question and answers. I was not looking at the chat. If somebody says something at the chat, sorry, I didn't see the chat. But I think this is moment for question and answers, okay?
Thank you, Professor Francisco. A very interesting presentation, and particularly the slides were very interesting and fascinating. We really enjoyed it. Any questions from the audience, please?
Oh, no people, not so many questions.
Sorry, may I jump in before a question?
Okay, I don't hear you.
Yeah, hello, Professor Francisco. First, thank you very much for joining us and delivering this very interesting presentation. I am Farad from the Western Australian IES section. I was very interested in this deep learning-based approach which you said in terms of improving the system condition. Can you elaborate a bit more on that? That generally, what was the story behind that, and how it was considering what parameters and how it is trying to improve the situation? Thank you.
I didn't hear you the first part of the question because it's quite loud. Could you repeat the question? Because I didn't follow the whole question. Sorry.
The question is mainly about this deep learning based technique that you had used for improving the system condition. I was interested to know generally which parameters were the key considered parameters there and how it was helping or improving the situation using this technique.
Okay, this is an amazing question. Thank you. It's quite interesting. I didn't go so many details because I was running out of time. But basically, our original idea was that you can have different energy storage technologies, and each one of those energy storage technologies, they have different speeds. I mean, if you send a command to produce 1 megawatt, this megawatt it will last different if you are using a supercapacitor, if you are using a flywheel, and you are using a classical battery, because depending of the technology, the state of charge will change differently. What we did, it was very simple. What we did is we took 3 different energy storage systems: battery, flywheel, and ultracapacitor, and we used an agent, and this agent was creating the actions. The actions were basically defining the power command for each one of the energy storage systems. But in order to define that, that very specific command, we use the agent in order to take some observations and reward, okay? The reward was defined basically a rule that depending how fast you reach some state of charge, if you reach the state of charge in a fast way, you compensate you provide reward in one direction. Or if you wait and discharge another energy storage asset, you can get another reward, okay? In general sense, what we did was create the reference for the different battery energy storage systems using a frequency rule, but at the same time considering the state of charge of the components, okay? And we reward those components if we discharge the energy storage system basic in reward rules, okay? We did this before using fuzzy logic. With fuzzy logic, we create the rules using the classical membership functions, triangular membership functions, and depending on that, we define the way to create the reference. But then when we use the reinforced learning, we were surprised that this agent, for the same case, was able to find better, let's say, power reference for the different energy storage system. And as a consequence, you reach, for the same frequency, you reach a better state of charge at the end of the period, okay? The focus of this paper was mainly technical. We didn't include cost, but remember that when you charge the battery, there is energy that you need to pay it, and also when you are selling the service, you need to compensate. That is another thing that we are working right now in order to improve the agent, but considering prices, market prices for the energy, okay? I think this explanation helped with this. I'm not sure if you need more details, but if you need more details, the link for the paper is downstairs, okay? It's over there.
Yeah, thank you. Thanks very much. That was very, very good and informative, and I really enjoyed the way that you had considered for that. Thank you very much.
Thank you. Thank you.
We have one more question in the chat box. Thanks, Professor Francisco, for the nice presentation. Wind farms with FRT capabilities are likely to deteriorate frequency regulation. Would you like to comment on this?
For many years, I have been working with frequency control, and I started to work with inertia for many years and try to get inertia from almost everything. Wind turbines, we try to get the inertial response from PV, from electric vehicles as well, for cluster of electric vehicles. Frequency regulations with wind power plants, it's a realistic option, okay? It's a realistic option if, and this is the big if you have the possibility of creating an artificial reserve for the wind farm, okay? And however, I'm not in favor of using these assets to produce frequency response, because with the prices of the energy storage system and the technology improving so fast, I think some countries around the world, they have used the concept of energy storage, collocation energy storage. That means every single renewable power plant has energy storage, and that solves many problems, including voltage regulation, including frequency control, and also in some cases even power or creating black star option for all technology for wind turbines. Okay. Now regarding the the frequency response of wind turbines, I think it's my opinion. It's my opinion that it's not the optimal option to improve the frequency in a very large power system. And the reason is basically you can have thousand of wind turbines, but the contribution of every single of those wind turbines is relatively small, and it's more complicated creating the whole contribution and coordinating the dispatch of that frequency regulation. Okay. Regarding the FRT, what I want to tell is that probably depend. Okay, I don't want to make comments in a very general sense. Okay, I am sure that the fall right through, it's an option that can be found in many wind turbines, but not at all the wind turbines. Okay. And also, even if we have a grid code for the fall right through, there is a partial interruption of the power production during the event, and that is debalancing the power system. What I'm trying to tell you is, okay, fire right through is a good characteristic that we want for short circuit events, but from the frequency point of view, the fall right through is just not, in my opinion, is not contributing so much for the improvement on the frequency regulation. Okay, that is my generic answer. Okay. However, I don't like to do generic answers because time to time, depending of the technology, grid code, and many other aspects, you can say something that could be grown in another context. In general sense, I am in favor of getting frequency response from power converters, but I'm not in favor of getting frequency response of all kind of technology. I have tried many technologies and they have different frequency response, and I am in favor of some of them, not so much in others. Okay, thank you. I don't know if this is helping with this specific question. Okay, but thank you.
Thank you, Professor. Any other question? So from Asma, thanks, Professor. I believe that more and more FRT capable wind farms are current requirements from TSO. This aspect also need more research.
Okay, I agree. Thank you very much, Asma, for this very important question again with the full road through. Yes, many utilities around the world, many companies are including the full road through in power converters. It's not only the wind farms, it's also HVDC interconnectors, it's also battery energy storage and so on. Okay, the full road through is probably not relevant if you have a large power system with strong interconnections. But when you start to have reduced inertia, one of the issues is that the voltage regulation start to be a problem when you are using the classical synchronous machine. And in this sense, the relationship between frequency and voltage start to be very dominant. Okay, I didn't tell in this presentation because it was a very informative presentation, but the connection between voltages and frequency in low or very low inertia systems start to be very, very high, and there is a strong connection. For that reason, yes, full road through is a capability that has impact, especially when you are working with very low inertia scenarios. I totally agree, require more and more research, okay? And just to close this question, for many years, the utilities has taken care about characterizing the loads, understanding the customers, and so on. No many utilities around the world have been involved in the frequency dependence of the loads. I know a couple utilities that they invest in research and understanding the frequency dependence of the loads. And some of them also scared about voltage instability. They do some research regarding the voltage dependence. I believe in the future, the contribution coming from the demand side in terms of voltage dependence and frequency dependence will be extremely important. And that is the reason I didn't tell about inertia estimation methods, but the inertia estimation method must be improved also there to cope and include more information from the demand side, especially with the new technologies, okay? Well, I think I overextend my time answering this question. I'm not sure if there is another one, otherwise, I'm not sure.
Yeah. Another message from Asma. Thanks, Professor. Nice to hear your valuable insights. Any further question? I can see one hands up. Yeah,
Yes,
please
from
go ahead.
Greece.
Yeah.
Yeah, good day. Just one question. According to your experience, is there any application or battery energy storage to improve stability in the transmission system level? I mean that the cost of storage system is very high, and the amounts of power or reactive power that needs to be injected or absorbed in order to stabilize a whole system, it's very huge. Or this solution is, let's say, restricted just to distribution networks?
Thank you very much for this amazing question. And I think this is one of the very useful questions that many people ask around the world, okay? Battery energy storage for transmission systems. In the case of the GB system, we have transmission levels of 400 kV and 272, okay? And this level for connecting directly a battery, they are not very, let's say, suitable for that, okay? For frequency control, what we love to do is installing the energy storage system as close as we can of demand side or generation side. And in the UK, there are many battery energy storage systems already in place, okay? I don't remember exactly the number today, 2021, but the last time that I remember properly is we used to have around 250 megawatts of batteries in the system, okay? Let me see, because I believe I have here a slide. Let me show you this slide over here that probably will make easy to everyone to understand the numbers about battery energy storage. Could you see this?
Yes, we can see the slide.
Yes, this slide. If you look at this slide, it's indicative numbers about the different energy storage technologies in the UK, okay? If you look on the right-hand side, you can see regarding batteries. And for 2020, the number it's supposed to be around 2,000 megawatts, okay? This is a number, you can see over here, it's around 2,000 megawatts of battery energy storage. And you can see how the number has been increasing over the years, okay? But also many people, when I was talking about the reinforcement learning, I was talking about different speeds of of the technologies, because for many years we have been having pump hydro or this pump storage energy storage system. And this is a very reliable, very useful for many decades. We have been using pump hydro power plants. Those pumps hydro power plants, they are installed and they are connected to transmission level, because you can see over here the power 2,300 megawatts. You can see over here 700 megawatts, okay? However, when we are talking about batteries, those 2 gigawatts over here, or the number of megawatts, they are spread around the system, okay? They are not directly connected to 400 kV. They are mainly connected to 132 or even less voltage depending on the system, okay? I cannot tell you the history about battery energy storage in other countries at the moment, but I believe this plot that I am presenting over here, it could be helpful for you to understand that, yes, there are installation of battery energy storage and also novel technologies like liquid air and their non-commercial operation, but for on the research in the GB system. I'm not sure if this helped. I hope this provides some insight about this.
Yes, perfect. Also, will you deliver the presentation? It's very valuable for us.
Yes, at the very beginning of my presentation, I tell to everyone that, as usual, I put my presentations in my YouTube channel. The recording will be available, okay? The recording will be available in a couple days in 4K resolution. And also, if you want to download the presentation, what you need to do is find my research gate, okay? Here I put on the screen, I hope you can see this. You can see this is the link for my YouTube channel, or basically what you need to follow, find is my surname, okay, Gonzalez Longat. And this is the link for ResearchGate. And hopefully in the next, I don't know, 24 or 48 hours, I will make available the presentation for downloading, and you can follow all the links to the papers and many other things, okay? I highly suggest, if you have time and you are interested to keep the track, I have a LinkedIn profile, and over there I announce many other presentations. In a couple of weeks, I will be talking about inertial response. And many people hate that I talk about inertial response because I criticize so much inertial response. Okay, any other question?
Thanks, Professor Francisco. Any other question from audience, please? Yeah. No further question, I think. Thank you, Professor Francisco, for joining us from Norway. Very great and interesting presentation. We really enjoyed it, and we have record attendees for and registration for this webinar. And thank you.
No, thank you very much.
Really appreciate it. We look forward to seeing everyone for the coming month IES webinar. Thank you, everyone. Thank you.
Thank you. Bye now.